Hello, Math 8 students. This is Utah Middle School Math Project 10.3a, Applications of the Pythagorean Theorem. We are going to get started with number 4. Is there anybody who plays baseball? Okay. And CJ actually plays catcher, so CJ knows. CJ, is it easier to throw from home plate, where you're catcher, to first base, or from home plate to second base? Why? It's a shorter distance, exactly. So this is a very applicable problem for CJ. Anyone else who might play baseball might find some value in this as well. We want to know, well, let's start with what we are told. Baseball diamond is actually not a diamond. It is a square. And because it's a square, we know that these angles are what? 90 degrees. They're right angles. They're 90 degrees. And it tells us that the distance between the bases, consecutive bases, meaning first to second, second to third, home plate to first, those are consecutive, meaning in a row. The distance between them is 90 feet. So from home to first is 90 feet. So first to second is going to be 90 feet. Second to third is going to be 90 feet, etc. Using that information, knowing that this is called applications of the Pythagorean Theorem, I wonder what we could use to help us figure out the distance from home plate to second base. When that catcher has to make that throw from home plate to second base, how far does it have to go? Chandon, what would you do? Yeah. Yeah. Mm-hmm. And instead of doing the whole hypotenuse thing, we would do the whole Pythagorean theorem thing, right? Which starts with a leg squared plus a leg squared is equal to the hypotenuse squared. So I did split it as I drew that line that the catcher would have to throw across from home plate to second base. Do you see, as Shannon pointed out, that splits it into two triangles? And do you see how this is a right angle in this triangle? So could we apply the Pythagorean theorem? Yeah. Because a leg is 90 feet and the other leg is 90 feet, so I can square those 90 feet, put them in the Pythagorean theorem, and what is it going to be equal to? The hypotenuse. Or in other words, I'm going to call it the distance this time because it's the distance from home plate to second base. So the distance squared. And 90 squared is equal to, Chandon again. Trinity. 8,100. Plus 90 squared, which I already know again, is 8,100. Add those up together, that will be equal to the distance squared. When I add them up together, Birdie. Fantastic. And that is equal to, once again, the distance squared. How do I get the distance to not be squared anymore? What do I do? Brighton. Yeah, square root. Whatever I do to one side, we do it to the other side. The square and the square root will undo each other, leaving me with just d, or the distance, which is equal to. And is the square root of 16,200 a nice number? No. But are we going to say, CJ, you need to throw the square root of 16,200 feet? No, that doesn't make sense, right? We would probably need to estimate that, or not even estimate, but approximate that. So let's type that into our calculator. Tell me what you get when you type that in. Tell me some of that big, long, ugly decimal. Chandon. A little bit slower. Just give me the first two decimal places. 0.27. Thank you. 0.279, he even said. So based on this, and based on the fact that it gave me 90 feet, which is 90.0, do you really think I need all of those extra decimals at the end? So we can probably round and just say 127.3 feet. Is that a perfect answer? No. So I'm going to say about 127.3 feet is the distance. Not a bad guess. Yeah, not a bad guess. But if it were exactly 120 feet, would they be right angles anymore? No. Okay, great job. Now, let's go back to number 3. We're going to draw a picture of this one. 2 ships leave a dock. The first ship travels 6 miles east and then 8 miles north, and it anchors for the night. The second ship travels 5 miles west and 12 miles south and anchors for the night. How far apart are each of the ships from the dock when they anchor for the night? This is so hard to understand what's happening until we draw a picture. So let's draw a picture. I'm going to start with, here's the dock. Let's review. North, if I'm drawing a map or on a piece of paper, north would be up. And then east and south and west, right? So the first ship travels 6 miles east and then 8 miles north. So I'm going to draw to the east. And I'm going to call that 6. I'm just approximating. We're not going for precision here. And it says 8 miles north. So again, I'm going to draw in the northerly direction. I'm going to say that's 8 miles. And there is ship number 1. I'll call it S number 1. This was the dock, so I'll call it D for the dock. Could you figure out how far away ship number 1 is from the dock? Yeah. Would I say it's 6 plus 8 away? No, that's how much it traveled. But how far away is it actually? We don't measure distance this way. We measure distance this way. And you might remember me saying throughout the whole entire year, we'll figure out how to measure distance like this later. We'll figure out how to measure distance like this later. And guess what? We know how, right? So how do I do this? Shannon helped us out with the last one. We'll pause the recording and let you guys discuss with your groups for a quick second so that we can come back together. How can I figure out how far away ship number 1 is from the dock? All right, let's start with Gavin, D. Okay. Everything that you're saying is so correct, but how do you know to just randomly start doing these things? What are we really applying? Which is called the, yeah, exactly, the Pythagorean Theorem. Because when I draw it like this, do you see a leg and a hypotenuse? So yeah, that's why what Gavin is describing is using the Pythagorean Theorem, where I take the leg and square it, take the other leg and square it, add them up together, and that's going to equal the hypotenuse. But what is it called again? This is going to be the distance. Yeah, this is the distance. So it's going to equal the distance squared. Perfect. So again, did you realize that this was going to be a Pythagorean theorem in the beginning? A Pythagorean theorem problem? Probably when you saw that it was Pythagorean theorem again, right? But really, truly, a problem like this, we forget that maybe we really do have all the tools that we need. So we draw a picture, we see the right triangle, and now we can solve. 6 squared is 36, 8 squared is 64, and that is equal to the distance squared. And 36 plus 64 is 100. Take the square root of each side. And how far away is that ship from the dock? 10, yeah. 10 what? 10 miles. Ship number 1 is 10 miles from the dock. All right, let's worry about ship number 2 now. Ship number 2, the second ship travels 5 miles west. And then 12 miles south. And anchors for the night. This is ship number 2. How far away is this ship from the dock? Can you answer that question? Again, do we really say it's 5 plus 12? No, that's how far it traveled, but how far is it really? We can find the hypotenuse of that triangle, which is going to be the distance, exactly. Yes, Kaden. Okay, let's baby step it. Let's show our work. Math practice 3 is construct viable arguments. That means we're showing our work. You just got math practiced. Okay. But let's go nice and slow for the video. A leg squared plus a leg squared is equal to the hypotenuse squared, or in other words, the distance squared. 5 squared is 25. And 12 squared is 144. We add those up together and it is equal to our distance squared. But 25 plus 144 adds up to be 169. So we take the square root of each side and we get a distance of 13, just as Caden said. The distance is equal to 13 miles. Okay, now voice is off. Let me draw your attention to these were story problems. Were they hard story problems? No. It's going to be interesting when these problems that are not stories are actually a little bit more difficult. Let's go back now and we're going to start with number 1. What is the length of the diagonal of a rectangle with side lengths 1 inch and 4 inch? And I can kind of get lost in that information until I realize, didn't these pictures really help us understand what was going on? All right, so let's draw a picture for number 1. What's the length of a diagonal of a rectangle? What should I be drawing? Probably a diagonal of a rectangle, exactly. Let's draw a rectangle and draw the diagonal. And is my rectangle drawn perfectly? No. But I know that a side length is going to be 1 inch and the other 4 inches. So am I going to draw this one, the 1 inch one? No, this is going to be the 1 inch. This is going to be the 4 inch. And it's asking what is the length of the diagonal. Do you see your right triangle now? Yeah, pretty easy, right? Go ahead and solve this. Again, I've got a leg, 1, which is going to be squared, plus another leg, 4, which is going to be squared. Leg squared plus leg squared is equal to the hypotenuse squared, or I'm going to call it the D for diagonal squared. 1 plus 16. Notice that I'm simplifying here, is equal to the diagonal squared. 1 plus 16 is equal to 17. 17 is equal to the diagonal squared. I take the square root of each side. Am I going to get a nice number here? Okay, pause. Can I have all fingers off calculators? Who has already typed this into their calculator? Okay, you don't get a chance to answer then. You get a zip it. I need you to, if you have not already input it into your calculator, it's time to use your brain. Is the square root of 17 going to be a nice number? No. So I want you to estimate first. The square root of 17 is kind of close to the square root of 16, right? What's the square root of 16? No calculators. What's the square root of 16? CJ? 4. We could also say that the square root of 17 is kind of close to the square root of 25. What's the square root of 25? 5. All right. So the square root of 17 is probably going to be somewhere between 4 and 5, right? Would you say it's closer to 4, like 4.1 or 4.2? Or would you say it's closer to 5, like 4.9 or 4.8? Yeah, we don't know for sure because we haven't typed it into our calculator, but could we estimate that it's probably going to be closer to 4 than 5? Okay, so what's your guess? Again, if you've already typed it into your calculator, you don't get to respond. What is that going to be? Have you typed it in? I'm not listening to you. Yes, you did. Who has not typed it into their calculator? I don't want to hear from you if you've typed it in. Liar. Liar. Okay. Luke, what do you think? Yes, I agree. It's going to be between 4 and 5. But 17 is a lot closer to 16 than it is to 25, right? So do you think it's going to be smack dab in the middle of 4 and 5? What would be a better estimate then? Probably, yeah. 4.3. Birdie, what are your thoughts? 4.3. All right, now go ahead and plug it in. What is the square root of 17? When you actually type it in, what is the square root of 17? CJ. 4.127? 123. And of course, there's lots of other numbers, right? Okay, that's... So, what is the length? Really, truly, we would say the square root of 17. However, we can say that is approximately 4.12. Okay? Yep, the about symbol is like an equal sign that's been squiggled. Okay, for the sake of time, do I want you to do number 2? Absolutely. But let's see if we can come back to it because there's a lot of other problems that I'd like to do. I want you to answer question 7. I'll read it for you and then I'm going to let you guys discuss, but I really need your attention and focus, please. Melanie is having a rectangular shaped patio built in her backyard. It is very important to Melanie that the corners of the patio are right angles. Remember in our video from Math Antics how they talked about the Pythagorean Theorem but also said it's a great way to test if it's a right triangle? You need to test if this is going to be right angles. Okay? The contractor built a patio with the width of 10 feet, a length of 15 feet, and a diagonal of 20 feet. Will the patio, or does this patio, have right angles? I want you to form a plan with your groups. Once again, we've seen how much drawing a picture can help, right, Stephen? So where should we start on this problem? Probably drawing a picture. Label the different parts that is given to you and then apply the Pythagorean theorem just like we have in these other problems. With your groups, I want you to work on number 7. Ready, set, go. Okay, here's my patio. 10 feet by 15 feet and a diagonal that is, come on, 20 feet. And we're questioning, is the Pythagorean theorem going to work here? Is this a right triangle? This would be where that right angle would have to be if it were, and it's going to be 10 squared for the leg plus 15 squared for the other leg. And we're asking the question, is that equal to 20 squared? So don't just say that it is equal, put a question mark like, is this equal? 10 squared is 100, 15 squared is 225, and 20 squared is 400. Again, I'm asking the question, is this equal instead of saying it is equal. 100 plus 225 is equal to 325. Is 325 equal to 400? No, this is false. So, if the Pythagorean theorem works for every right triangle and it's not working here, is this a right triangle? No, this is not a right angle. Her contractor needs to go back to probably building school and junior high school. So. Okay. All right, as much as I love problem number 8 and even problem number 9, we're going to skip them for now. If we have time at the end, we're going to come back to them. But I want to focus on another concept, using the Pythagorean theorem to find distance between points. Again, I have mentioned when I would talk about like the distance between these points, I would say it's down 2 and over 4. That would be how I would have to talk about the distance because we couldn't measure the actual distance, but we can now. So when I look at segment B, I guess, and I ask you to find the length, your first instinct should be make it into a triangle. Make it into a right triangle. So drop it down. Go across, and when you actually draw it, can you see the right triangle now? And now we can use the Pythagorean theorem to figure out how long segment B really is. What is the leg? 2. And the other leg? 4. There's not a whole lot of space. It's not really great, so you just kind of have to squeeze your work in wherever. I'm going to squeeze the work in just right up here. A leg of 2 is squared. Added to the leg of 4, which is also squared, and that together should equal segment B squared. 2 squared is 4. 4 squared is 16, and 4 plus 16 is 20, and that's going to equal that B squared. So we take the square root of each side. What's that? Yeah, it's not a nice number. Probably another good time to estimate. The square root of 20, probably going to be between 4 and 5. You want to guess 4.5? It's probably a good guess now, 4.5. And When I actually calculate the square root of 20, it is not a nice number. We could simplify this, and let's do that. You guys remember how to do that from a couple lessons ago? What are the factors of 20? 4 and 5. 5 is already done. 4 is 2 and 2. Do you see a pair? Yep, so 20 can be written as 2 squared times 5. And when you take the square root, what's the square root of 2 squared? 2. What's the square root of 5? It's the square root of 5, right? So we could say b is equal to the square root of 20. We can simplify to 2 square roots of 5, or we could say that is about, what is it? When you actually plug in square root of 20, 4 point what? 47. You could say 4.5, yeah. I usually like to say, unless it's like a measurement problem like that baseball problem, I think it's okay to go at least 2 decimal places. But I'm not picky about that. All right. Will you guys take a second? Will you, no, just do C. Yeah, do C. With your groups, do C. We're going to pause the recording as students work on this with their groups. All right, and there is segment C. C is equal to the square root of 10, which is about 3.16 units. Okay, so let's move on to these ones. What if I just said, what's the distance between A and B? What would you do? It's the same type of problem, right? What's the distance between A and B? What should you do? Birdie. Okay, draw a line from point A to B. Now what? Exactly. Make it into a right triangle. And when I make it into a right triangle, I'm going to be drawing a leg that goes straight down. That leg has a length of 2. Another leg that goes straight across, and that leg has a length of 5. That's exactly what I would do too. If I'm asking you to find the distance between those 2 points, we know, let's draw that distance, and then we see, hey, wait a second, that looks like a hypotenuse. If that looks like a hypotenuse, that means I could probably use the Pythagorean Theorem, and so I do. 2 squared plus 5 squared is equal to that distance squared. So once again, I like to use the variable d for the distance squared. 2 squared is 4. 5 squared is 25. And that is equal to that distance squared. 4 plus 25 is equal to 29. And that is equal to d squared. Watch me estimate again. I do not have the time to plug this in. You guys can see I am still just writing the entire time. But I know that 29, the square root of 29 is going to be kind of close to the square root of 25. Not quite the square root of 36. So I'm going to say it's probably around 5.4-ish is my guess. 5.38. Okay. So d is equal to the square root of 29, which is about 5.38. Yeah, it's okay if you round it. I would give yourself 2 decimals and round. Yeah. Okay, could you do number 3? I'm not going to make you. I want to move on to a little bit more challenging problem. Look at this one now. There's no longer a grid, right? But could I still figure out the distance? Let's do like Birdie said. Let's first draw that line that goes between them. That's the distance that I'm trying to find, and hey, that looks like a hypotenuse, doesn't it? So let's draw the legs. One leg is going to go straight across. One leg is going to come straight down. The challenge is I don't have a grid, so I can't just count how long that is. But there is information there that we can use. Where is that information? Like, how can I figure out how long this purple side is? A few hands. What would you do, Chandon? Mm-hmm. Kind of. So I am lazy. I could graph it out, but really what you're suggesting then is if this is 4550, then that means I need to try and draw 45 lines before I get to there, right? Okay, or how long is this segment? So think about this, that all the information that we need is right here. Without us having to draw anything extra, we can still do it. What does this 45, 50 mean? They are the coordinates, but what does it mean? What does that mean, where it's at? Where is it at, exactly? Birdie? Yeah, but I want really specific. Where is it? What does this number mean? On the x-axis, we moved over 45. On the y-axis, we moved up 50. Okay? So where is this point? It starts at 45, and it's up 50. Where is this point? 100 to the... Okay. So if we were at 45 and now I'm over 100, how far over did I have to travel? In other words, how long is this purple line? Brighton? It is 55. Do you see where he got that information? We were at 45. We had to move over until we got to 100. So how far over is that? It's 55. Okay. Where is this point? This is up 50, right? How high up am I going to get up to here? 80. So how long is this line? 30, exactly. So can you still find it even when you don't have a grid to count? Yeah, you just got to pay attention to your x coordinates and your y coordinates. Seeing that these x coordinates tell us how long this leg is, and the y coordinates tell us how long that leg is. Let's complete that problem then. 55 squared is one leg. 30 squared for our other leg, and that is equal to the distance squared. I'm not going to be successful with these ones. Help me out. 55 squared. Thank you, Birdie. $302.25? 3,025? 3025, like that? Okay, 3025. And 30 squared, I'm going to guess that that's 900. And it is equal to the distance squared. When I add those up together, I end up with 3,925 is equal to the distance squared. I take the square root of each side, and I get the distance is equal to... Luke, do you have that calculated for me already? D is about 62.6. Give me one more decimal. 64. Great. Not too hard, right? Does it take some good visualization skills? Yeah. Understanding what those coordinates mean. Here's your real challenge. Look at A. Could you put these points on a grid and then do it? Yeah. No, go ahead. Go ahead. Yeah. Exactly. So if I'm going from 3 to 6, what is that distance? That's going to be a distance of 3 or a leg of 3. Keep going. 5. Exactly. So again, that means that the leg of this one goes from 5 to 9. So how long is that one? 4. So do you have to use grid paper or put it on a graph to answer these questions? No, we can just use that other strategy. Yeah, these numbers work out nicely. 3, 4, 5. I already know it's going to be 5, but let's use that Pythagorean theorem to prove it. One leg is 3, so we square it. The other leg is 4, so we square that. We add them together, and that is equal to the hypotenuse squared. 3 squared is 9. 4 squared is 16. 9 plus 16 is equal to the hypotenuse squared, and 9 plus 16 simplifies to 25. Take the square root of each side, and we get a hypotenuse of 5. Okay, now we do have some extra time, so we are going to return to problem number 8, this application. This is going to touch on some concepts that we are going to be practicing a little bit later on. This is volume of a cone. So Sunny made a paper cone to hold candy for favors for a baby shower. After making the cone, she measures the slant height of the cone and the diameter of the base of the cone. Her measurements are shown in this picture. So a few things that we need to remember, because again, we're finding the volume of the cone. This length right here is the diameter. Sunny also measured what is called the slant height. So it's not the true height of the cone, it's if we're measuring along the side. So this is the slant height. Okay. The next thing, I actually want to switch that to a different color. The next thing that I would like to review with you guys is, okay, this is not deleting like I want it to. The next thing I want to review with you guys is area of a circle, because we need to know area of a circle so that we can actually answer this problem. Because when I am finding the volume of a cone is equal to 1/3 times the height times the base. And when we talk about the height, we're not talking about the slant height. What we're talking about is the actual height. Can you see how I basically formed a triangle here? Okay, so we still need this measurement here, this height. We need that to be this. But I also want you to understand the base would be the area of this circle. Let's go back to 7th grade. How do we find the area of a circle? What do you remember, Kaden M? No, that would be if it's a rectangle. Length times width if it's a rectangle, but this is a circle. How do we find area of a circle? Other Kaden? No, we don't go across. Nope. Last one, and then we have to actually finish this problem, so let's try Luke. Yes, good job. Pi r squared, great memory. The base is equal to pi r squared. What does the r represent? The radius, yes. The r represents the radius. Do we know what the radius is in this problem? No, they gave us the diameter. Can you find the radius that goes from here to here? How do you find that radius? It's half. So 3.5, half of 3.5 is 1.75. We have calculators, we can use them. Okay, voice is off. So let's first find the area of this circle. How do we do that? Pi times the radius squared. So the radius is 1.75. We're going to square that and multiply it by pi. We're not actually going to type that in just yet. But what does this b actually represent? It's going to be pi times 1.75 squared. We're almost ready to use this formula. We just need to find the height, right? How do I find the height? Do you see anything that might have anything to do with the Pythagorean theorem here? Yeah, we have a leg squared plus a leg squared is equal to a hypotenuse squared. But the leg squared this time is going to be the height squared. Plus, look at this. The other leg is the radius squared. And that is going to equal my slant height, or the hypotenuse squared. So can we solve this to figure out the height? Yep. 1.75 squared. Help me out with these calculations. I don't know what that is. I do know what 5 squared is, so I can do that. 25 is equal to h squared plus 1.75 squared. Who has 1.75 squared? Thank you, Gavin. 3.06 exactly? Will you give me a few extra decimals on that one, actually? 3.0625. Thank you. Plus the height squared. Okay, we haven't solved problems like this today. We solved them last time. But do you see how we've got to get h squared by itself first by subtracting that? So let's subtract that 3.0625 from each side. I really have not left myself enough room here. Whatever I do to one side, I do it to the other side. So that has zeroed out. And again, I need your help with these calculations. I have the h squared, the height squared, is equal to 25 minus 3.0625. Birdie? 21.9275. 9375. Thank you. And we take the square root of that. And that is going to be equal to the height. The height is equal to the square root of 21.9375. Not going to be a nice number, so we'll just keep it like that. What is the height? The square root of 21.9375. And now we can finally type this all into the calculator. So we're going to type in 1/3 times the square root of 21.9375. Then make sure you're out of the square root part. It's all up there. So I have the fraction 1/3 times the square root of 21.9375. I'm going to go outside of the square root, type in that number pi, multiplied by 1.75 squared, and that is quite a lot in the calculator. Do you guys see that? And we get 15.02, or about 15 inches cubed, because it's inches times inches times inches, volume is inches cubed. That was intense, right? Which is why I didn't assign it as homework. You guys know what your homework is. It's been assigned. Thanks for watching. We'll see you next time.